Intramolecular dehydration. Alcohols are dehydrated intramolecularly to form alkenes when heated with sulfuric acid. And so in this dehydration reaction, basically you lose a water, which is why they call it dehydration, and you form a double bond. Some alcohols can produce two different alkenes. With ethanol, there's only one possible product. But here, we protonate this OH group, and then it leaves, creating a carbocation. And now you have a choice. Either this hydrogen can pop off, and these electrons can come in forming a double bond here, or the same thing can happen to this hydrogen over here. So you have actually two choices of alkenes which you can make, and these electrons would come in here. So you can form two different alkenes. In this case, the major product will be the most substituted one. So notice in this one, each of the carbons has a methyl group coming off of it. So there's two substituents coming off of the carbons with double bonds. Whereas in this one, just one carbon substituent's coming off. And so here's a hydrogen and here's two hydrogens. The more highly substituted product is the more stable one, and that's the one you'll form. And that's Zaitsev's rule. It can be used to predict the major product in a dehydration reaction. If there is a choice of positions for the carbon-carbon double bond, the preferred location is the one that generally gives the more highly substituted alkene. That is the alkene with the most alkyl or carbon-based groups, organic groups, attached to the double bonded carbons. That will be your major product. You'll always have a few percent of the minor product, but this will be the major product. So what are the products when 2-methyl-2-butanol is dehydrated with sulfuric acid? Well, again, the first step is use the acid because it protonates the alcohol group, and then water leaves, giving us this carbocation. And now this hydrogen can pop off. Oops. To form that double bond that you see here. Or one of these two carbons, they're both identical, so it doesn't matter which one you choose. One of those carbons has a hydrogen, and that hydrogen can pop off, and those electrons could come in here, forming this product. This is the more substituted one. You have 1, 2, 3 carbon groups coming off the double bonded carbons. Whereas in this one, we only have 1, 2. So again, the more substituted product is the major product because of Zaitsev's rule. Intermolecular dehydration. Ethers can be prepared by an intermolecular dehydration between two primary alcohol molecules when heated with sulfuric acid. And basically two alcohols react to form an ether and water. So this is a dehydration synthesis. Also sometimes called a condensation reaction because you're spitting out a water molecule. So what ether is formed when two molecules of butanol react through intermolecular dehydration? Well, we react here, we get two of these butane groups connected at carbon number 2 bound together. So this came from one of the butanols, and then this came from the other. And then a water is also expelled. And again, if we look at that mechanistically, you're using acid. When you have an alcohol and acid, think protonation for oxonium. This O, those electrons grab this hydrogen, and now we have oxonium. And then these electrons go to it, and water floats away, leaving this molecule. This now will bind another of these butanols. So let's pretend it's a different butanol now. Now these electrons in this oxygen attack the carbocation, and the H plus floats away, giving us our product, and that's how it happens. Esterification. Alcohols react with carboxylic acids to form esters. And then so this OR group basically replaces the OH group. And what you end with is an ester. And so this is found here. And we spit out a water molecule. So acetic acid is condensed with ethanol. We get ethyl acetate, which is a common solvent in organic chemistry, and it's used in a lot of nail polish removers, so you've probably actually smelt it before and would recognize it if you smelt it again. Some nail polish removers use acetone, some use ethyl acetate, but those are the two major ones that you see used in the industry. Three important reactions involve the hydroxyl functional group. We get oxidation to aldehydes, ketones, and carboxylic acids. We get dehydrations to alkenes and ethers, and esterifications to esters. So there are three general methods for synthesizing an alcohol. We can either hydrolyze an ester to get the alcohol back. We can alkaline hydrolysis an alkyl halide, so an OH minus slams into a carbon, kicking off like a chloride or a bromide or an iodide, giving you the alcohol. Or the catalytic reduction of aldehydes and ketones. And for those last two, only primary and secondary alcohols work, because the tertiary, with the alkyl halides, they're too sterically hindered. So if you have like this molecule, there's no way the OH can attack actually. These molecules are all in the way and it's blocked from attacking, so there's no chemical reaction there. And then you can't have a tertiary aldehyde or ketone, because to have an aldehyde or ketone you have to have two bonds to an oxygen in some form. A ketone, there's two carbon bonds, and in an aldehyde there's a hydrogen and a carbon, but still you can only have two other things bound to it. So if you reduce this, you're only going to get a primary alcohol or a secondary alcohol. But there's no way you can have three carbon things based off the carbon, because you need two bonds to the oxygen, only leaving you two other bonds. And so you don't get tertiary alcohols from reduction because the starting material is impossible. So for that to work, you'd have to start with 5 bonds on carbon, which you cannot do. And so that's why you don't get tertiary alcohols from this. Hydrolysis of an ester. Water can attack an ester, and that water comes in, hits this carbon. Those electrons come up here. They come back down to reclose your ketone group, kicking off your alcohol. That is hydrolysis of an ester. It can be acid catalyzed or it can be base catalyzed. They both work. So alkane hydrolysis of an alkyl halide. In this case, our OH minus comes from the other side, slams into this carbon, kicking off that chlorine, which is exactly what happens to form the alcohol and the sodium chloride. Catalytic reduction of aldehydes and ketones. We can reduce on hydrogen and nickel. You can use palladium or platinum. They're actually even better than nickel. Nickel works, but it takes really high temperatures and high pressures, whereas with platinum and palladium, you can get the same reaction at a much lower pressure of hydrogen gas and a much lower temperature. But nickel's a lot cheaper, so there's pros and cons to each catalytic system. And aldehydes will produce primary alcohols. Ketones will produce secondary alcohols, because the aldehyde is terminal, so it's only connected to one carbon group, and the ketone has two carbon groups, making it secondary. The preparation of methanol. Methanol is a common industrial solvent prepared by the high-pressure catalytic hydrogenation of carbon monoxide. And so this is a form of synthesis gas in which carbon monoxide and hydrogen gas are reacted at super high temperature. That's like 400 Celsius. Very high pressure, 200 atmospheres. So 200 times more pressure than what you get at the surface of the Earth with zinc oxide chromate catalysts, and you can get methanol out of this reaction mixture. Properties and applications of methanol. Boiling point, 65 degrees Celsius. It's a highly flammable liquid. It's poisonous and can cause blindness or death if someone swallows it, because in the liver it's oxidized to formaldehyde, which is a potent cross-linker. And then that cross-linker can actually bind the alpha-crystalline proteins of the eyes, and it clouds them over, and so a person can't see through their eye lens anymore. And so you have to be careful with methanol, because it is poisonous and it does cause blindness. As little as drinking 10 milliliters can definitely cause blindness in a person. So it does not take a whole lot. It's pretty potent poison. Applications. It is a feedstock chemical to produce formaldehyde. It's a good industrial solvent, and we use it to denature ethanol. When we say denature, what we mean is ethanol is being sold, but whoever is selling or buying it doesn't want to pay the drinking tax on drinkable alcohol. And so a poison is purposely added so no one can drink it, and therefore it's no longer drinkable alcohol, and therefore it's no longer taxed as drinkable alcohol. So denaturing ethanol is literally poisoning it on purpose so that it is not drinkable, so that you don't have to pay taxes on the alcohol as if it was drinkable. Preparation of ethanol. Ethanol can also be prepared by acid-catalyzed addition of water to ethylene. Properties and applications of ethanol. Boiling point, 78 degrees. It's very hygroscopic, which means it actually takes water out of the air. And so if you have 100% ethanol and let it sit out, it'll start soaking up water vapor from the air until it's down to a concentration of 95.6 ethanol. Depending on the quantity consumed, it can be considered a drug or a poison. And again, it is poisonous if enough of it is consumed. It is a depressant, and in the end, it depresses a person's respiratory system so that they actually stop breathing, and that's the cause of death from alcohol overdose. Ethanol is used as a solvent for many organic substances and a compounding ingredient for pharmaceuticals, perfumes, flavorings, and is a major component in alcoholic beverages. And these days, it's one of the major compounds in gasoline. And so most gasoline is typically 10% ethanol in the United States. And then you can get more ethanol, like E30 is up to 30%, E50, E85 has huge amounts of ethanol because it's a good fuel and it burns really cleanly. Preparation of 2-propanol, which is isopropyl alcohol or rubbing alcohol. Propene, acid-catalyzed addition of water, gives you isopropanol or 2-propanol. It's called rubbing alcohol because people rub it on people when they have a fever, and the evaporation of the alcohol, it feels good, it cools a person off. That being said, care should be taken. If someone's too young, they can get alcohol poisoning from this. So it's not a good idea to be rubbing a lot of rubbing alcohol on a small child because it's still absorbed through the skin in some amount, and that can actually be really dangerous for a small child. Applications of 2-propanol. We can oxidize it into acetone, which is a major industrial solvent, or we use it as rubbing alcohol. Preparation of ethylene glycol. Ethylene glycol is a diol obtained from petroleum or prepared from ethylene oxide. And this is antifreeze. Ethylene glycol is what you put, it's what antifreeze is made out of, and it goes in your car. It works as a coolant or an antifreeze. It's also a useful solvent for paints, plastics, and ink applications. It's poisonous, it destroys the kidneys, and it's sweet to the taste, which actually what makes ethylene glycol very dangerous. Because if it spills, animals or kids might eat it and die from it. And so always take great care with ethylene glycol, because it has the unfortunate combination of being both sweet and poisonous, and that makes something dangerous to children and animals. Properties and applications of glycerol. That's 3 carbons with 3 OH groups. It has good water solubility. We can manufacture polymers and explosives from it. It's used as an emulsifier in cosmetics, which is something that blends 2 other chemicals together that don't normally mix into each other. And it can be used as a sweetener. Here we see a picture of nitroglycerin, which is extremely explosive.